So in 14.3, number 36, they want to find the volume of this solid. Z equals log of x squared plus y squared. Z equals the natural log of x squared plus y squared is a boundary. Z equals 0 is a boundary. And then they have these other little funny phrases. So that's a boundary. This is a boundary. And you know what? Just real quick, I would kind of guess that that's my bottom and that's my top. You know, I mean, I have this is the good old XY plane, and then this is some surface above the XY plane. And then they tell me this, that x squared plus y squared better be greater than or equal to 1. And they also say x squared plus y squared better be less than or equal to 4. Well then, see, okay, so I've got a good picture of this in my brain. I mean, when I read these equations, I kind of know what's going on. Again, I feel like this is some top, and I don't care to really draw that exactly. So I got some top, if you don't mind. The z equals 0 is the floor, the xy plane. And then this is you guys should know, this is a cylinder of radius 1. And then this is a cylinder of radius 2. You know, with no z there, these are, you might call them circles of radius 1, a circle of radius 2, but with no z, then they're cylinders. They run up and down the z-axis. And they say I'm greater than that one and less than that one, so I'm in between these two cylinders. And right. So this is this shape. I've got this funny shape here. Kind of the cylinder with a hole cut out in the middle of it. And the surface above me here is whatever this log surface is. That's my ceiling. That's my ceiling. That's my top. So I'm ready to go. And maybe I really didn't need this 3D picture. I tried my best to draw you one. I know it kind of sucks. But what I need then, I think, to do volume, I would do a double integral. And if I'm doing a double integral, and I'm doing volume, then I need a function in here. This function is my ceiling. This function would be this function. I also think, based on all this that's going on here, I should do all this in polar. So as I set this up, I'm going to put it in polar coordinates. So here comes this surface, ln, the ln of, but I'm going to call it r squared, right, the ln of r squared. That's my ln there, sorry. Exactly, ln of r squared. And then the dA has that extra r, dr, d theta. And then I'm working on integrating between these two cylinders, between these two circles, so to speak. You know, I can see it there, or I could blow up and look at a blown up picture of the XY plane. But it's just the same picture. It's a circle. It's this stuff in between these two circles. So I think R goes from, can you give me bounds for R?
1 to 2?
Yes, from 1 to 2. That leaves out the 0 to 1 there. It sure does. From 1 to 2 leaves out the 0 to 1 we don't want. And then theta, 0 to 2 pi. And that's it. This will be the volume of this weird shaped thing. So, I think that was a rather easy setup. So look for that. That's not bad. Now, if we got to do this, maybe that isn't that easy. Let me think. How do I do? First of all, I'm integrating log. That's very rare and weird. I mean, that's kind of rare and weird. So I could help you do it, but I don't think I'd ask you to be that weird on a test.
Oh, okay, then I'm not worried about it.
Well. I mean, things could show up on tests. I mean, integration by parts could show up. The tabular method could show up. I mean, some different weird things could show up. But integrating a log does require integration by parts.
Oh, you can't use that?
And you can't really use the tabular method shortcut. So you got to use the integration by parts. Anyway, maybe, again, it'd be fun to sort of finish it and go off on that, but I can almost promise that it ain't on the test.
Could you do the U-substitution?
Well, the U-substitution would be kind of nice. It would lead you to the log of U. But then how do you integrate the log of U? You still would do integration by parts.
I'm thinking of the absolute value of ln, which is 1 over the argument.
That's the derivative of ln.
Right.
We're trying to integrate ln. Right. So, the derivative of ln is 1 over. And if you had a 1 over and had to integrate that, you'd get an answer of ln.
Right.
Okay, but integrating ln is weird. I think you should let u equal the ln of r squared. I think dv equals the r, dr. That's that r, dr. I think what you do is you take a derivative right here. That's 1 over r squared times the derivative inside, 2r dr. What you do right here is you integrate, and you get 1/2 r squared. And that seems kind of weird, but that's how you do this problem. Here we go. The answer now is the integral of uv. Wait a minute. How do you do integration by parts? You got the integral of u dv equals uv minus the integral of v du. So the answer is uv minus the integral of v du. When I put this all together, the 1/2 and the 2 are going to cancel. The r squared is going to cancel with that r squared. I'm going to have an r dr. Can you integrate that?
Yep.
R squared over 2. So here we go. So now I integrate that, and it's r squared over 2. Anyway, that's the answer to this integral. And I had to do integration by parts and know a little bit about what I was doing to get there.
So you might actually have that kind of thing on the test.
Usually if I have integration by parts on a test, it's the tabular method, and it's kind of, but
The textbook has like a shortcut to the integration by part. It has like an acronym, LIATE. Logarithmic, inverse, trigonometric,
Yeah.
algebraic, and
Okay.
geometric.
all that is a hint on if you're staring at at an integration by parts problem and you're not sure who to let u equal.
Yeah.
That's the order in which you let u equal things. So at the top of that list is the L for logarithm. So when you decide you got to do this by integration by parts, you also decide that you're going to let u equal the logarithm, and dv is going to be the other thing. Which is counterintuitive. Most integration by parts, you let u be this, because then you take its derivative and let it go away. See what I did with this, I let it be dv and then it grew. It went from an r to an r squared. But with the log involved, that's how they work. They work differently than other integration by parts. But now we're into a deep discussion on integration by parts that isn't the point of chapter 14. But that, it's okay. We love all math, of course. But so I guess I'm going to pause halfway through this one here. By the way, this is the answer to the inner integral. Let me just show you how quickly it ends. I'm not going to finish it. But then you throw your 1 and your 2 in there, apparently. You evaluate it from 1 to 2. It looks like to me it'll be, whatever it is, it'll be a number. So then the next step will be to integrate with respect to theta, which will throw a theta on there. From 0 to 2 pi, throw a 2 pi in there. So you can almost, you put your numbers in here and then multiply by 2 pi. The end happens quick and easy.
I think it's 22.619. 22.619.
Okay.
But that could be wrong.
Okay. I I like these problems in the 30s. And she asked me about 36. It wasn't my favorite one here, but I helped you get started. These ideas will come up. Integrating this won't come up, but these ideas come up. These two circles like this comes up on the test. So there's some value here to this problem here, but we're just not going to do that integral. But you know what else is good here is this 39, and there's one on your take-home quiz like this. So either I could do 39, or I could do one on your take-home quiz, or I could do one
On the take-home.
similar to the take-home quiz. Oh, there it is. Here's one called 59. See, 59 is awesome. Here. 59 from 12.3 says, determine the diameter of a hole that is drilled vertically through the center of a solid that's bounded by these graphs. And so one of the graphs is z equals 25 e to the negative x squared plus y squared over 4. Z equals 0 is a boundary, and then another boundary is x squared plus y squared equals 16. All right, listen, there's some directions on here that I read real quickly. So this is a solid. This is a solid, and maybe I need to draw a picture of it. But then what they want me to do is drill a hole through the middle of this solid and remove 1/10 of the volume. So I've got my work cut out for me on this problem, but I think what I ought to do first is maybe get a picture of it and start thinking about the volume of it before I worry about drilling a hole and removing some of it. Let me just think about the volume of this. Well, first of all, again, maybe you don't need a full 3D picture. I mean, isn't it kind of clear who's the top and who's the bottom? I mean, this is, whatever this is, it's on top and this is on the bottom. This is the XY plane, and then this is my surface. So I've got some surface above the XY plane. And then this must be some, again, a cylinder of radius 4. This must be some side boundaries. I mean, again, pretty kind of similar to that picture, except there's not two cylinders. There's just one cylinder of radius 4. The truth is, you haven't maybe seen this shape too much. This is a cool shape. This is, it's sort of a mountain here. If you plugged in 0, 0, you'd have e to the 0, and you'd get 25. So at 0, 0, it's at 25. But then it comes down and tapers off toward the x-axis, or I'm sorry, it tapers off toward the XY plane in all directions. So it's a little mountain is what it is. It's a beautiful little mountain. At 0, 0, it's at its peak of 25, and then as it tapers off in all directions like a mountain. And then we're bounded out here by a radius 4 cylinder here. So we're going up and hitting this mountain. The picture's getting messy. The picture's getting messy. But can you sort of see what I'm saying? There's a surface and there's these cylindrical walls. I've got this sort of cylindrical radius 4 cylindrical walls, and then I got this top. So if you wanted the volume of it, I think you would do a double integral. Who would you integrate?
Z.
This Z right here. Do you think you want to put it in polar coordinates?
Yes.
What makes you think that?
X squared plus y squared.
That x squared plus y squared makes you think you want to put it in polar coordinates.
Also the cylinder.
Okay, I think more importantly, Zach and anybody, is you're right, that kind of is a hint that you might want to go to polar, but I think the more important hint is the region over which you're integrating, which is this circle of radius 4, kind of from here. So because I'm integrating over a circular region, yeah, I'm going to switch to polar. In other words, this same shape over some kind of triangular region, you might not want to switch to polar. Right. But over this circular region, I think we'll switch it to polar. So if I switch it to polar, this becomes 25e to the negative r squared over 4, right, you guys? Mm-hmm. It's that easy. I'm going to put an r d theta here. Dude, this is so easy. Now I need bounds for r. Can you look at my xy plane and tell me the bounds for r?
0 to 4.
Thank you. 0 to 4. I mean, again, usually I draw a separate picture for you to look at the region over which you're integrating, but there's the region over which I'm integrating. Yeah, 0 to 4 for r. Theta, please.
0 to 2.
All right, awesome. Now, what is this? This is the entire volume of this entire thing. Now, what they want me to do, and maybe I need this, maybe I need to do this, but hang on. What they want me to do is find the diameter, or I might go for the radius, of a hole drilled through the middle so you remove 1/10 of the volume. So I'm going to say you drill a hole through the middle of it, and you're going to remove, and I'm going to call it radius A, an unknown A, radius A, and I'm drilling this hole out of the middle of this, and so that red stuff is going to be 1/10 of the volume. All right, so now I feel like I want to set up an integral for the hole. Okay, so what's the hole? All right, well, guess what? Okay, who's the top? Is there a top surface above that hole? It's the same mountain. The top of the shape was this equation. The top of the hole is still that equation. So I'm still integrating the same function.
Just go with 0 to A.
Thank you, but now I'm integrating over this small little region, 0 to A, 0 to an unknown A, and then 0 to 2 pi. Are you guys with me?
Mm-hmm.
Now hold on. This is the hole, this is the entire volume, so they shouldn't be equal. Hang on a second. One of them is 1/10 the other one, or one of them is 10 times the other one. You can, let me think. The hole's the small one, right?
Mm-hmm.
So if I just multiply it by 10, now they're equal?
Yeah.
Yeah, now they're equal.
Could you
Or I could have multiplied this by 1/10.
could you evaluate the right side and subtract the left side's evaluation?
Well, hang on a second. I'm not sure. First, I'm setting up the concept of the problem, which is that I've got this unknown radius A, but if I integrate, this is the hole, and if I want the hole to be 1/10 of the entire volume, then if you take the hole and multiply by 10, you will get what we set up as the entire volume. So what I have set up here is an equation. This is what's so beautiful about this problem. I have an equation set up with an unknown variable, A. And your job is to solve for A. You know what I mean? I mean, it's like back in intermediate algebra when we used to go like this. Okay, kids, solve for A.
1.
Very good. Well, it's just like that. It's exactly like that. Here's an equation. Please solve for A. That's the way we've set this up. It's very cool, except it involves, instead of intermediate algebra, it involves some double integrals. But it's still just an equation, and we're looking for this radius A. That'll be the radius of the hole. Technically, the way that the question was asked, they wanted the diameter. But once I find this radius, I'll multiply by 2. So I think to do this problem, you need to do this integral. But what's kind of cool is it's practically the same integral, except over here you've got real numbers. Over here you're going to be plugging in an unknown number called A. Hey, do you know the last step of doing this integral? I mean, I think there's a lot of work to do, and we've got to plug in some numbers. And then the last step is going to be integrate with respect to theta. And I think we'll probably throw a theta on it, and then we'll plug in 0 to 2 pi, so then we'll probably throw a 2 pi on it. Guess what? Over on this side, I think the same thing happens. Well, at the very end, first we'll have some crap going on, but then we'll integrate with respect to theta, We'll throw a theta, we'll throw a 2 pi on it. Are you with me? All right, because of those two, I'm going to just go like this. I'm canceling that. I feel like the result of that, I just had to read into the future there quite a ways, but the result of that is that there's going to be a 2 pi on my answer on both sides of this equation, so I can just cancel my 2 pi's.
So do you cancel the d theta as well?
Well, right, so I've sort of turned this into a single integral maybe here, right. I mean, I'm just not going to integrate that last part. Yeah, you're right, good idea. Probably should cancel that d theta, right. I'm just not going to do that last part. The last part just generates a 2 pi on both sides, which I'll then cancel, so I'm not going to bother. Seeing that coming, I'm just not going to bother. But I do have to integrate this and get a number, and I mean, this stuff, I mean, it takes some work here. But I like this question. It's on your take-home quiz, and I don't know, sometimes it makes the test, sometimes it doesn't. Let's work on this a little bit. You know, these E integrals are kind of easy. You have one of these on your quiz like this with an R squared and an R here. Technically, you should let U equal the negative R squared over 4, I guess, because it's going to be an E to the U. But then what's du? Du is negative 2R over 4 dr. Or you could call that negative a half. I think I'll multiply the negative 2 to the other side. Negative 2 du equals R dr. You follow that? You call something U, you find du, negative 2R over 4, yeah. That's negative 1/2, you multiply it to the other side, and then you replace all this junk. So here I am on this side, let's see, how's this junk getting replaced? It turns into 25 e to the u, I think. What about that R dr? How am I replacing that? Oh, there it is. R dr gets replaced by a negative 2 du, technically, right?
Yeah.
And so I'm going to put the negative 2 out front and put the du here. Okay, now, can I integrate? Sure. When you integrate e to the u, you get e to the u. So I'm going to call that negative 50 e to the u, but I'm going to go ahead and put u back. Negative R squared over 4. And what are my bounds for R? 0 to 4. So it really wasn't that hard, was it? I just did that little U-substitution and did that integral. I think I did everything right. Let's see what happens. When you plug in the 4, that's a negative 16 over 4. It's a negative 4. It's negative 50 e to the negative 4. Minus negative 50 e to the 0. And e to the 0 is 1. So that, right, this negative sign came out here, but this answer is not negative. This ends up being a positive 50, which I'll write in front, minus this 50 over e to the 4th.
Where'd that second 50 come from?
Well, plugging in a 0
Okay, gotcha.
is not always a 0. Plugging in a 0 is e to the 0, which is 1, right. Cool, that's the answer to that integral. What does it equal? It equals the answer to this integral. All right, hang on. What's the answer? Ain't this the same thing? It's totally the same thing. What's it gonna be? So it's going to be a negative 50. Except don't forget there's a 10 out there, right? I better keep that. There's a 10 out there too. There's a 10 out there. And then there's a negative 50 e to the negative r squared over 4. I mean, I sort of skipped everything. I just do this integral the same way you would. Right. Same exact problem. Except there's a 10 out there. And now let's evaluate it from 0 to a. Let's evaluate it from 0 to a. Okay. So maybe negative 500 e to the negative a squared over 4. That's what happens when you plug an a in for r. And then minus, when you plug in a 0, you're going to be minusing a negative 500. So if you don't mind, I'm going to call that a positive 500 minus this thing, which is 500 e to the negative a squared over 4. It all equals 50 minus this 50 over e to the fourth here. Yeah, remember what I said? It's just solve for a. Okay, we're finally here. We had to fight through those double integrals, but now we're here. We want to solve for a. That's an a right there. Any suggestions? Subtract 500?
Yeah.
Subtract 500.
I
Okay,
think we should
subtract.
divide by 50 first, though.
Well, all right, there's a lot of things. All right, I'm subtracting 500. That's negative 450 minus 50 over e to the fourth. Yeah. Over e to the fourth. This equals this negative 500 e to the negative a squared over 4. You want to divide by negative 500? Let's divide by negative 500. Right? Trying to solve for a. Divide by negative 500. First I subtracted negative 500. Now I'm dividing by negative 500. Dividing by negative 500. Whatever. So I got e to the negative a squared over 4 on this side equals, I'm going to just call that 9/10. And it is positive 9/10. And the other thing is a 1/10 plus 1/10. And then that e to the 4 is down there. I might want to move that. If I move that e to the 4 up, it's e to the negative 4, right, you guys? E to the negative 4. Now they have a common denominator of 10. Now what? How do you solve for a?
ln both sides.
Yes, ln both sides. Negative a squared over 4 equals the ln of this. Great, 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 great. Multiply by 4? Multiply by negative 4, I guess.
Yeah.
Multiply by negative 4 and then take the square root. So a is the square root of negative 4 times the natural log of 9/10 minus plus e to the negative 4 over 10. Wow, that's amazing. That's
So
it.
ln of 9 plus e to the negative 4 over 10
Sure.
is negative.
And then it's multiplied by a negative 4, thank God, which makes it positive. And so then the square root of
Is
this
it
positive
imaginary?
number is some little positive number.
See, 9 plus e to the negative 4 divided by 10. ln of that answer times the negative 4, yep, it was negative, to the 1/2, 0.64, 28919.
So A is 0.6428, blah, blah, blah. Again, that's the radius. So the answer to the back of the book would be the diameter, which would be double that. Cool. Anyway, I like that problem. Now, what's fun at the end is some. This is just some good exponential logarithm algebra here at the end. This is prior to that we had to do a double integral, sort of. But prior to that, we had to set the concept up. We had to set it up with an unknown radius a. I like that. That's setting up. So that's cool. You can find it. You found the radius that removes 1/10 of the volume. That's awesome. So you got one on your take-home quiz like that. Maybe almost exactly like that. What does it say? I don't care. I'm not going to redo that one now. But it's the numbers are a little different. Not much though. Not much, but a little different. Yeah, I mean, also it's not 1/10, it's 1/3. Yeah, so number 11 is a lot like that. That's good. That's good though. What else? Anything else? Any other good questions?
Yeah, number 9 on 14.3, I think they use like a double angle identity. I just got confused with that.
Number 9. Oh, they do. Yeah. Yeah. I got you. Number 9 and 14.3 is just an easy little integral, but then it Right, it runs into something that we haven't really seen before. 0 to cos theta, 0 to pi. Well, we haven't seen it in this class. Let's see. So what happens? You integrate with respect to r squared over 2. You plug in cos theta, and you get cosine squared theta. Right. So the answer is 1/2 cos squared theta. Right. And then you're trying to integrate with respect to theta from 0 to pi. And how the hell do you integrate cos squared? Right, there's only one way to integrate cos squared. I learned it in Cal 2. I could have learned it in Cal 1. It's just a memorized formula. It's just a trig identity. It's called the half angle formula or the double angle formula, or that we call it the half angle formula. So let me see, do I remember it? Let me see if I can remember it. The half angle formula for cosine squared is, now this half is already here, but the half angle formula I think has another half, 1 plus cosine 2 theta. Yep, so a cos squared turns into this. This is already here, and now you can integrate it. So that's, we learned that in Cal 2. It's just kind of weird. It's just the only way to integrate cos squared is you use this funny half angle formula. It's not even that famous, but it's a manipulated half angle formula from trig. It's an identity that we've manipulated and use in this place for this purpose to help me integrate cos squared. Let's just finish it. That's a 1/4, and when you integrate the 1, you get a theta. And when you integrate a cos 2 theta, I think you get a sine 2 theta, but it spits out a half. You guys okay with that? Mm-hmm. So there we are, and now we try to go from 0 to pi. Let's see what happens. Plugging in a pi, we get 1/4 times pi plus, but see, this is going to be the sine of 2 pi, and the sine of 2 pi is nothing. Minus, and then we plug in a 0, and that's a 0, and the sine of 0 is 0. So I get more nothings. So the answer is right here, pi over 4.
So cos 2 pi is equal to negative sine squared of, not cos 2 pi. Sorry, cos 2 theta is equal to negative sine squared of theta?
Oh, I don't know about that.
1/2.
Where are you coming up with that?
Yeah, you're right.
I mean, I integrated between this step and this step. I integrated.
Well,
Between this step and this step, I used an identity.
Well, I was wrong for sure because I forgot the 1/2. But I was looking at because cos squared equals 1 minus sine squared of theta.
Yeah, that's true.
I was looking at the 1 plus cos 2 theta and trying to make that have some sort of equivalence to it. There's that 1/2 out front.
Right.
I guess you could. Yeah, you really can't. I mean, you could say.
Right.
Doesn't really work.
Right. It's just its own separate identity. It comes from this. When I learned trig, it was called the half angle identity, and it looked like this. It's called the half angle identity. It looked like this. This angle is half whatever that angle is. But you could say this angle's double whatever this angle is. And so another way to write this is if I just make this a theta, then inside here is a 2 theta. Is that okay with you? So that's one trick we did. And then the other thing we did is we squared both sides to get rid of the square root. So when you square both sides, you just get rid of the square root, you get rid of the and now you have this. And that is exactly what I said. I said cos squared theta is this. I memorize it like this to help me integrate. But officially it came from some old half angle formula in trig is kind of where it came from. What were we doing? Oh, he asked about this number 9. Right, because he ran into a cos squared. How do you integrate a cos squared? Right. That's it. I mean, by itself. I mean, we could turn this chapter into reminding you guys how to integrate things. I mean, but but this is different, like a cos squared with a sine sitting here.
Yeah.
See, that's, then I would let u equal cosine, I think.
Mhm.
And du is negative sine, is that right?
Yeah.
Yeah, and then, so then that kind of kills this, and so now I get a u squared, right? It's a u squared with a negative sign out front, and when you integrate, it's 1/3 u cubed, and so anyway, there's different scenarios, but when that cos squared is all by itself, there's only kind of one way to do it, this half angle formula. One of my other favorite problems, and it shows up here on your take home as number 6. So on your take home quiz, number 6. But maybe I don't want to really do number 6. So here's what I want to do. I want to do this. I want to find the volume of the intersection of x squared plus y squared equals 9. No. X squared plus z squared equals 9, and y squared plus z squared equals 9.
Or R.
Well, right. So
So you're modifying,
right. I'm modifying number 6. That's right. Right. So your number 6 has an unknown radius r. Mine has a radius 3. But see, this problem came from the book, and maybe in the book it was radius 1, and they didn't word it like this. And this was in, this might have been in 14.2, number 37. Somewhere, one day I told you, hey, my favorite problem is here. And then we just never got around to it, so maybe we should do it now. And what is this? Well, like I said, in number 6, it's described very well for you. When you first are presented, you might not know what this is, but you know, these are these circles of radius 3, but it's a circle in the xz plane. Y is missing, so it's a circle in the xz plane, radius 3, running out the y-axis. So it's a cylinder running out the y-axis. Radius 3. Now here's the deal. I don't want to draw the whole cylinder. I want to, the picture gets messy. So I want to stay in the first octant here. So I got a quarter of a cylinder here. And it's headed off in this, right. Okay, what's this one? Oh, that's a cylinder of radius 3 with x missing. He's running out the x-axis. He's hitting, in the yz plane, he's hitting z at 3 and y at 3. And then he's running out at me. So he's coming out, he's a quarter of a cylinder running out at me. And then where they meet, so this cylinder is bending this way, this cylinder is running this way, and then when they meet, there's a little cliff or wiggle right. Did you hear that? There's a little crease here, kind of. See, now I got a good looking picture of this. Now, in number 6, I asked for the intersection at right angles of 2 pipes. So that's what this is, except this is only, I'm only in the first octant. I think this is 1/8 of it.
So you have to multiply by 8.
Is this, I think this, do you agree with me? Maybe you can't, again, I kind of rushed through this because I'm rushing through everything today, but let's try this. Let me try it better. Hang on. So I'm saying there's this pipe going this way, and then there's, Jesus, there's this pipe coming this way. Yeah, that clarifies everything. You know, what we should do is take a field trip to the plumbing aisle at Home Depot. Because you see these in the PVC section, you can find what's called a cross. I think they call it a cross when it's not a T. A T is a T. This is a cross where 4 things can come into this, and 4 pipes can come into this. And so I'm just kind of looking at, Jesus. You know, if you look down on it, so what's interesting is the base is square. I mean, the equator is sort of square, as you can sort of see. Again, this is only 1/4 of it. See, it's over here too, and it's back here too. It's back here, and then there's other pipes. Jesus. That ain't bad in a way. I mean, that's kind of it. That's sort of the top half of it. But again, we're just looking at, okay, that's the top half, and we're looking at 1/4 of the top half. We're looking at 1/8 of the whole thing when I'm looking in the first octave. That's kind of a mess, but it is kind of like, yeah, that's kind of the top half of it. See, my z-axis is coming up here. My x and my y-axis are here. And so I'm looking at just this. And then this, I got this border coming here. You with me?
Mm-hmm.
Okay, cool. Now I'm getting better. So one more time. What was this? 3, 3, 1/4 of a cylinder coming out this way, and 1/4 of a cylinder coming out this way. There's this crease here. Now here's the deal. Which one is who? I mean, this guy is this one that's bending this way. He's hitting the YZ plane. So the name of this top is the y squared plus the z squared equals 9. This one is hitting the x and z axis. And so if he's hitting the x-z axis, then he's this guy. He's the x squared plus z squared equals 9. All right, so we're saying I want the volume of this and multiply by 8. Can I really just do half of this?
Could.
Let's just do half of this. I mean, the truth is, to do this, I got to split it into 2 anyway, because his ceiling has a name. If I solve for z, his ceiling has a certain name. The other guy is a different name. It's a different ceiling. So I'd have to do 2 different integrals to do these 2 different ceilings. So let's just do one of these and multiply by 16. So let's do this one. So now I'm doing this. All right, this ain't going to be too bad, you guys. I'm going to set up a double integral. That's it. I'm going to multiply by 16. And who am I integrating? What am I integrating? Well, I'm integrating this top. Okay, what's the name of this top? Okay, there's the name of this top. But I'm supposed to solve for z. Z is the square root. And it'd be plus or minus, but I think we're up here. We'll take the positive square root. The positive square root of 9 minus x squared. Right, you guys? Mm-hmm. Okay, that's what I'm integrating. And then I can do this dy dx or dx dy. Or maybe in polar coordinates. I don't know what you think. I'm going to write down dy dx for the moment. Oh, I mean, there's a lot of circular stuff going on here. These cylinders are circular cylinders, but the region over which I'm integrating is this triangle. I want to stay in x's and y's. This is not a polar problem, right? That's why I was in 14 too, actually, right? Okay, good. So now I just got to analyze. This ain't bad, dude. All I need now is the bounds for this region, right? You know how to do a double integral. You need the bounds for the region. And that's a nice little region. You know that this line, what do you know the name of this line that I cut right here?
Y equals x.
It is. It's right through the middle there. It's a good, perfect diagonal, 45. It's y equals x. So let me get my 2D picture. Here's my 2D picture. In the xy plane, I've got, hang on, which one am I doing? Am I doing the one that's bordering the x-axis? Is that what I'm doing? Yeah, look, mine's bordering the x-axis, right?
Yeah.
Mm-hmm.
All right, so that's the one I'm doing. Right. And this is named y equals x. So I decided I wanted y to go first, I think. So what's the bounds for y?
it's x minus 3.
The bounds for y. The bounds for y. My y bounds
I think it's 0.
go from this thing called y equals 0 up to this thing called y equals x. And then you leave off the y equals and you put 0 to x.
Right.
Right. And then x, bounds for x, please. After y does that, x goes from
0 to 3.
Dude, we got it. Multiply by 16, and we have the intersection of two pipes of radius 3. The actual intersection of two pipes of radius 3. The entire intersection of two pipes of radius 3. Which is kind of cool. I mean, if you worked for the sewer company, you might need to know this, right? These big sewers with radius 3 feet. Radius 3 feet? Yeah, that's pretty good. You could walk through them if you wanted to.
So are you finding like the volume of how much water it can hold?
Well, I'm finding the volume of space. It could hold jello or water or air or whatever it holds. It'll be its volume of space, right?
You could find the maximum
And then-
volume throughout the flow rate.
And then this is just through this intersection, though. I mean, this is just in this intersection, which is this funny room. It's this funny shaped room. And by the way, this is only half the room, right? I mean, the bottom of the room looks just like this, right? Jesus. Sorry. I mean, there's a mirror image of this below this, right? So this isn't a very fun room to walk around in. You're walking around down here. But the volume of this thing, right, there it is. That was a cool problem. I like that problem. Your question, your number 6, just makes you deal with a radius r. So
Could we, I mean,
what would be different? You'd have a big capital R squared here, and treat it like a constant. You'd have a big capital R squared here, and you have to treat it like a constant. In the end, I think your answer will have a big capital R in it. You know, that your answer will have a big capital R in your answer.
I'm sorry.
That's okay.
Is there any way to do it, for example, like I did for the take-home quiz, without using, without just doing a 16th of it?
No,
No, there isn't. Okay. Well, guess
I don't
should
think so.
start
The way I broke this down with these pictures, I've broken it down into, let's do an 1/8 of it. And then if you're doing this corner of it, you're going to have to do 2 anyway, kind of. Well, or listen, first of all, there's a hell of a lot of symmetry going on here. So doing half of this, you know it's the same as the other half, right? So I like the concept of doing a 16th of it. I've divided this funny thing into 16 little chunks, and I'm doing the volume of one of them and multiplying by 16, right? Hey, you want to finish it? It's easy to finish, kind of. At first, I got scared when I put this in here. I thought, damn, I don't like this. Is going to be hard to integrate. But hold on, you're integrating with respect to y, so keep in mind how easy that is. This is a big constant. When you integrate with respect to y, you get the big constant times y. And then the bounds are 0 to x. So then you're plugging in an x. So now you end up with this. And it's nice that that x showed up there. You know that. I mean, if you've, from the U-substitution that we need to do, that x is important to be there. So right, now the next integral is with respect to x, and I'll use U-substitution to finish this. You guys okay? I mean, we can finish it. You let u equal the 9 minus x squared, of course. The du is the negative 2x dx. That takes care of that x dx for me. Let me see, how do I do this? I turn it into a square root of u. Now what about the x dx? The x dx is du, except I need to move the 2 over, the negative 1/2 du. I mean, that's how I do it, right? I better write that for you so you understand what I'm doing. Right, I solve for what I'm replacing. I'm replacing the x dx with what it says it is. X dx is this. So it's 1/2, negative 1/2 du. Oh yeah, don't forget there's a 16 out there. Okay. You guys okay? You followed me through there? And now we integrate. U to the 1/2 is what that is. U to the 1/2. So when you integrate, it's U to the 3/2 times 2/3 times a negative 1/2 times a 16, right? So those 2's cancel. I'm getting a negative 16/3, and this is 9 minus x squared. Is that what it was? Yep. To the 3/2 from 0 to 3. Here comes the good part. When you plug in the 3, you get a 0. When you plug in the 3, you get a 0. When you plug in the 0, you get a negative, but it's subtracting a negative, 16/3. When you plug in the 0, you get 9 to the 3/2. But that 9 is, hang on, that's the square root of 9 cubed. The square root of 9 is a 3. When you cube it, it's 27. And then it's over this 3, which makes it a 9. So shit, I think this is 144. That's cool.
So
This is 144
16
cubic feet.
So it's 16 r cubed over 3, in a way.
Is that what he just told me? He's telling me he's telling y'all the answer to number 6. Is that what he's doing? The radius, hang on. The radius is 3 squared. The squareds cancel, so you end up with 3 cubed. So you're saying it's 16 r cubed over 3.
I got the right answer. I did not use that method.
Yeah, you might have done something right. Or sometimes if you do 2 things wrong, you end up back at right.
That's also possible.
I mean, maybe you did something else. Did you set up a double integral?
Yes. 8, I did the whole first octave. The inside of the integral, or the inner integral was the square root of r squared minus x squared.
Right.
That inner integral's bounds was 0 to the square root of r squared minus x squared. And then the outer integral was 0 to r.
Right, that would have been true. And you had an 8 out here.
Yeah.
But you had different you had this funny different bound. What do you do?
I think I was.
See, you were thinking you were sort of treated this as circular here. Maybe.
Oh, I knew what I did.
You might want to look at your work.
I
But
don't,
anyway.
I don't think I made a. I don't think I did it like this. I did it like this.
Oh, how?
One vertical, one coming along the
Okay, gotcha.
along one of the axes. Can't exactly tell which.
So how would that make it different?
Looks like I had one in the z
So
axis.
you did have. So you would sort
I
of
would
have a
have
circular boundary. That is kind of interesting. Okay. Yeah, you might be onto something. You might be onto something. So now, did you still try to work in quadrant 1?
Yeah.
So this will be cruising through here. Let me just use my 3's here for a second. So, all right, this will be my sort of my top, and then my. So where's my? Yeah, I'm having a hard time seeing this now. So your square is kind of running. Now you might want to do it in polar.
Yeah, I can see where polar would make this.
So you're still integrating this top.
But I think I probably didn't like the idea of polar because I wanted that radius in there. I don't think polar would give me a radius. I don't mind. So that dr would be there.
Yeah, that might be onto something. So now what happens? When you integrate this, you get a y, right? You get this times y. And now you're plugging this in for y. That's kind of cool. So you integrate, you get a y. Then you plug this in for y, which means you knock off your square root. So now you have this. Now you integrate 9x minus 1/3 x cubed.
Yep.
From 0 to 3. You get 27 minus 9. You get 18 times this 8. What's that, 144? Yep.
Yep.
I'll be damned. Good job, Zachary. You did it different. That's pretty cool. Good thing you told me, or I might have marked you wrong. Yeah, I think that makes sense. I'm having a hard time seeing it though, because I've always looked at it like this. I looked at it sideways. I can't turn my head. It just should, should just be able to turn your head. All right, cool. That is interesting. It wasn't that hard. I mean, even though I was tempted to go to polar, I'm glad I didn't, maybe. I mean, that square root killed that square root. Huh. All right, what else? Anything else?
14.3, number 20.
14.3, number 20.
Yeah.
Yeah. Ooh. Well, yeah. Yeah, maybe we could learn something from that. Got a 2 there, so I see something there. It's funny. In 14.3, number 20, they just give you this double integral, and it's x squared plus y squared, and it's yep, dy dx. But then they've got these nasty bounds. Negative square root of x minus x squared to the positive square root of x minus x squared from 0 to 1, I think it says. Yeah. Yep. So, now, and by the way, and then they say switch to polar. Do this in polar. So, you know, you can switch to polar. It's easy, pretty easy to switch to polar. This is an r squared, and then this comes with the extra r dr d theta, which actually then you join these, you end up calling that r cubed, of course, and you integrate, you go ahead. So that was nothing to that except, so here's the hard part, these bounds. What the hell are these? What is this region? See, in order to switch the bounds, you really kind of need to see this region and then rethink this region in polar coordinates.
It's a line.
Well, not really, no. I mean, you know, one way to see this region is pick up your graphing calculator. This is y, and then you can type in y equals and see what these are, maybe. I'm going to suggest that what you have is these.
Yep.
So I think one of these is this top half of this square root, and the other one is the negative square root. This is y equals the positive square root, and y equals the negative square root. So really it's just a circle of radius 1 diameter 1, radius a half, I guess. sitting off to the side like that. And in polar coordinates, I happen to know his name. When he's sitting out there with a diameter of 1 sitting off to the side, then in polar coordinates, he's r equals 1 cos theta. The diameter 1 cos theta. That's the name of that in polar coordinates. That makes you recall a little polar coordinates. Let's say you didn't recall that. You ready? Watch this. Let's say you don't recall that and you're trying to convert to polar. Well, what you've got is this. Okay, you guys? And you're trying to convert to polar. Well, square both sides. Add the x squared over here. You guys with me? Mm-hmm. Now convert to polar. That's r squared. And by the way, x was always, it doesn't seem like we've used this too often, but you might need this. You know, x is r cos theta. Y is r sine theta. So x is r cos theta. Okay, well I just converted him to polar. And now if you divide out in r, that's one way to solve for r here. You divide out in r, and r equals cos theta. So, yeah, there he is. Sort of proven to you. So if I'm setting this up for polar coordinates, this is the region over which I'm integrating. I figured that out maybe by using my graphing calculator or knowing about these shapes. But now, thinking this through with polar coordinates, r goes from the origin out. R goes from the origin out. R goes from the origin out. So I think no matter what r is, it goes out and it hits this. So I think my bounds for r are 0 to cos theta. I mean, that's my, from the origin out to the curve, and the curve is named this. Cool. And then for theta, you could get yourself confused. Maybe not. It's kind of obvious. It would be wrong to go from 0 to 2 pi. It would be wrong to go from 0 to 2 pi. It might seem like you want to go from 0 all the way around to 2 pi. But that actually plots out this circle twice when you do that. You'd end up with double the area. So these circles that are sit off to the side, they don't need 2 pi to get plotted out. They only need pi. So you could do 0 to pi, that would do it. But really any interval of pi would do it. You know, maybe you look at this picture and maybe it's more reasonable for you to go from negative pi over 2 to pi over 2. I mean, maybe you think of it as living over there from negative pi over 2 to pi over 2. But the truth is, 0 to pi would work. From 0 to pi over 2, it plots out these points. From pi over 2 to pi, you get negative values for r. Negative values for r put you over here. So from 0 to pi over 2, it plots out that. And then from pi over 2 to pi, it actually does plot out these points. So 0 to pi works. 0 to pi works. But it's not wrong to put negative pi over 2 to pi over 2. Or like I said, I think any interval of pi would work. 3 pi over 2 to 5 pi over 2. But putting 2 pi on there would be wrong. So I just helped you. The main thing was helping you with this. What the hell is this? And if you call it y and use your graphing calculator, you can sort of see it. But what it is it's just an off-centered circle. You convert it to polar by doing this. You know, in rectangular, you do this. You move this x over here, and you complete the square. You add half of this. Oh yeah, you find half of this number, which is a half, square it. So you add a 1/4 right here to complete the square. Well, you better add a 1/4 to the other side. Now this is a completed square. You know what it is? It's x minus 1/2 squared plus y squared equals 1/4. Now, if you're good, you can stare at that and say, oh, dude, that's a circle centered at 1/2, 0, radius 1/2. Which is what we said. I mean, it's so funny how you can say the same thing 6 different ways.
Like in,
Anyway, that damn x means you got this off-centered circle, and completing the square kind of leads you to it if you want to. But the truth is, I don't want to be here. I want to be in polar, so I went to polar as quick as I could here. I still needed these ideas to get me to polar, though. You know, it's a big game you play. Well, maybe we're at the end of class. So, I don't know, study hard. I think this is a harder test. It's just, you know, it's not me, it's just the material. Chapter 14.